Hello everyone, welcome back to the channel Chemistry for IIT JEE. Today we are starting the discussion of IIT JEE 2023 papers, and we are doing it a little bit different than most of the video solutions online are there. Different in the sense that we are going to have elaborated solutions where we will be not just talking about which option is correct and why this option is correct. We'll be diving deep into every single option, every single aspect which was probably given in the problem. The reason behind that is we get a comprehensive idea about the question being asked and the things related with the problem. So we are starting with the paper number 1, and we'll be going in serial wise manner, like first question, second question, third question, like that. So the first section we are going ahead is with the one or more than one correct questions. We're marking scheme as per JEE is +4 for the correct options and -2 for incorrect and 0 for not attempted. And if you have partially attempted, then there is going to be partial marks like +1, +2, +3 or +4 depending upon how you responded. So the very first question was from Metallurgy. This is question number 1 from paper number 1. So in Metallurgy, they tested students basically on 3 different aspects. Number 1, what are the names these ores correspond to, and what are the processes involved, like what is the meaning of roasting, calcination, and what is there happening in the reverberatory furnace. So these first points, the first 3 points were related with the pyrometallurgy, and the fourth option, this was pyrometallurgy. The fourth option was related with hydrometallurgy. So basically in a single question, they have asked many things what they could possibly have asked. So starting from roasting, we know what roasting implies and what calcination implies. One is heating things in enough supply of oxygen. Calcination is heating in very limited supply or no supply of oxygen at all. And then when we are heating things with the silica in reverberatory furnace, that is basically to remove impurity and all. We are trying to do pyrometallurgy where we want to convert our copper pyrite ore into some different products. So copper pyrite is basically the ore of copper. We want to extract copper. So other impurities, whatever will be present there, we want to get rid of. Like here they are saying that iron can be removed using silica in the reverberatory furnace. That was one of the idea. And the last option was about the hydrometallurgy, which is basically the leaching process in which the potassium cyanide or sodium cyanides are being used, and they can be used for complex formation and then ultimately reduction of that silver complex by zinc metal into the metallic silver. So many concepts put together into a single question, the expertise of JEE. Here we go. The very first option, malachite. So what malachite is? Malachite is some green colored ore which is having chemical composition of CuCO3.CuOH twice. That is, we can say basic copper carbonate. And this is green, like similar to what we have seen the color of copper carbonate. If you have cupric carbonate, that is also having green color. And the reason when we try to look into deep, that reason why malachite is green while the number of different compounds of copper, like copper hydroxide or different compounds, are found to be blue in color. So we have a reasoning that carbonate is a relatively weaker ligand in comparison to hydroxide. So this will be absorbing on lower wavelength of that Vibgyor spectrum in the visible region what we are having. So in the color wheel, the color which will be observed will be corresponding to longer wavelength in comparison to blue color. And that longer wavelength in comparison to blue color is coming very next to that one is green. That is how we explain the color of why malachite is green. Later we'll be seeing there is a very closely related ore which is called azurite, which is blue in color. We'll be seeing that in a moment. So that is the color of your malachite, which is a very brilliant green, beautiful green, different shades we see. We'll see that in a moment again. And this name is basically coming from the resemblance of its green color to the mallow plant, which is having the leaves of mallow plants were having similar pattern as we find in the naturally in the malachite ores in different places. Also, we are talking about roasting in the question. So when we are doing roasting, and roasting is heating in excess supply of air so that there is enough oxygen present. Yeah, and usually we are doing this for the sulfide ores where oxidative roasting basically we are doing where oxygen is getting into our sample. So what this is doing, this is converting our green colored malachite into black colored cupric oxide. And that black colored cupric oxide, what is being formed, this one can be reduced further into metallic copper by carbon reduction or any other suitable reducing agent. Mostly that has been carbon, which was used traditionally from very long time. So that cuprite, what they referred to in the very first option, is not this thing. This is cupric oxide. And cuprite is basically the oxide ore of copper, which is basically a minor ore, usually does not found in nature in abundant amounts. So that option, what they want you to say, when malachite is heated, this basically this is roasted, this is producing cuprite, that is technically not possible because malachite is having copper 2 and carbonate and hydroxide. None of the carbonate or hydroxide are found to be reducing in nature. And when you are roasting it, during roasting process, you are providing oxygen that is supposed to be oxidative process. So there is no possibility that copper 2 plus, which was present in the beginning in the malachite, can be converting into copper 1. That kind of process is simply not possible, right? So this first option cannot be correct. This is going to be incorrect. That is how cuprite looks like. That is Cu2O, cuprous oxide. Also, there is something not very much right in this option number 1, option number 2. Why I'm saying that? Because when we refer to cuprite, we are talking about the ore of copper which exists in nature. And when we are doing metallurgical operations, like when we are doing roasting of malachite, what processed ore we are getting? For that processed ore, the name could have been used, cuprous oxide is formed or cupric oxide is formed. When they say malachite is being heated and cuprite is formed, that is something technically wrong. That does not happen, although the cuprous oxide is not being formed. Even if this would have been formed, saying that the malachite upon roasting gives cuprite would not have been correct, even if that would have been somehow formed. That we'll be seeing in the second option when they are saying that calamine is being heated and this is producing zincite. So technically that is not valid because zincite and cuprite we are using for ore. We are not using for the processed or when they're converting to some chemical compositions later on. Okay, very much related to the malachite will be the one ore we will be calling that azurite. Here is the stages what have been traditionally known for the malachite when it was happening. So there are different stages of the reduction of the malachite. So green colored malachite is first of all being reduced to the black colored cupric oxide when we are roasting, and then that roasted cupric oxide finally when this is being reduced by charcoal reduction or coal based reduction. So the color change, you can see the green color is converting into black color. So malachite is currently cupric oxide, and then we're getting characteristic copper red colored metallic copper upon reduction in the next step or the subsequent step. Here it is how it happens. So basically you are going from left to right, that's malachite. This one is being converted into the black colored cupric oxide. This is your cupric oxide, and then this upon being further reduced with the carbon-based reducing agents, charcoal or coke, this is being converted into metallic copper. That is characteristic red color of the copper in the pure state. This diagram has been taken from Journal of Chemical Education. That has the volume number and issue number, and this is coming from the paper reported by Yee and Eddleton and Johnson. So basically this method of the reduction of malachite to copper has been known from very, very, very long time. 4000 BC, these processes were known to the people different places. Okay, going further, we have got very beautiful green color of this malachite, which has been used in different artifacts like flower vase and other different artifacts like this beautiful green colored elephant carved differently. You can see the beautiful patterns of the light blue and like green, turquoise, whatever those different colors are. I'm not very much familiar with all those different colors, but there are very full colored patterns over here you can see. And those kind of patterns are actually found in many of different ore samples, not just malachite. Different ore samples are also excellent. Malachite is having characteristically this kind of patterns present in almost all of the ores. And of course, we are using this in different kind of gemstones, and people say, they proclaim they are having some magical healing powers. Although I don't believe in all those kind of bullshits. There are people out there who still believe, and people even have been believing. So historical uses of this malachite include talisman for young people who were supposedly believing that this is protecting them from different things, like they are helping them sleep, they are protecting them from the lightning which is happening, and the contagious diseases, as if they might have cured them from the coronavirus. Probably all the world population would have used malachite to get saved from the COVID if that was the case. That is, I'm sarcastically speaking. I don't believe in all those kind of things. Maybe there may be people who can keep believing. I don't care. And they also have been using this for good health and success, and more surprisingly for constancy in relations. Okay, actually for constancy in relations, some other things are required other than just wearing these stones or gifting these stones. Okay, that's not my domain. Let us move on to the next thing. That's azurite. Azurite is having beautiful this blue color, and these are the different ores of the azurite collected from different samples, and this is the powdered azurite which have been used in different pigments. Powdered azurite, this one. So chemically, this is very much closely related to the malachite, but this is having 2 times copper carbonate and 1 cupric hydroxide, that is having different color, and this color is attributed to what we understand the DD transition, which was supposed to be there in the copper plus 2, as we are having in different situations for the different copper plus 2 salts. The next option about this question was calamine upon being heated gives zincite. On the top over here, we are having calamine, and over here we are having zincite. Again, as I was telling you earlier, zincite is the term we are using when this is present as the ore. When we are processing zinc carbonate, and zinc calamine is chemically ZnCO3, which upon being heated is supposed to be converted into zinc oxide. So if you do calcination process, calcination is basically heating in absence or very limited supply of air. So you are getting zinc carbonate. Thermal decomposition of zinc carbonate is giving you ZnO plus CO2. That's a chemical change we might have seen already a number of times. ZnCO3 is like calcium carbonate, upon heating converts into ZnO plus CO2. So this zinc oxide, what is left, this is the processed ore. Now for the processed ore, we have never been using the term zincite. Understanding the idea, they thought about the question, they probably wanted us to know what is the zincite ore. So whether that zincite ore is matching to the option or not, that is what they wanted to a student to think. Okay, we can go ahead with that thought, and we can believe that calamine upon being heated will produce zincite. If you are believing that zincite is the name of the ore, which can be having a number of different impurities as well, which is naturally present, we are not getting that thing. Like the processed ore, we are getting a different texture of zinc oxide which would be there. It will never looking like this, which is zincite present in nature. Okay. Also, we understand that this zincite is having some yellowish color, although we understand that ZnO is supposed to be colorless as per crystal field theory, because this is D10 configuration and this should not be having any color. But then in the solid state, students do learn that when there are some defects present in our crystals, like non-stoichiometric defects where some oxygen is being lost, that's going to be some metal excess defect. So in that metal excess defect, when a zinc is present in excess, this is going to produce some color, and the color of the hot zinc oxide, if you do in lab, it is found to be yellow in color. But this kind of brilliant yellow color we don't see in the natural, in the sample in the lab when we are processing calamine to get the zincite. That kind of color is coming from the natural settings, where one of the reasons can be the non-stoichiometric defects present in the natural specimens. Apart from that, sometimes there can be the impurities of some other trace elements like Fe3 plus or things like that. So there can be different reasons for the color of the zincite, which was supposedly going to be or supposed to be colorless as ZnO. So this option we can believe to be true, because they probably wanted us to know that when ZnCO3 is heated, that is being calcinated, what was the supposedly product being formed. ZnO is being formed. ZnO is also called zincite, so they related. They expected student could relate and they can believe this statement is correct. We are believing it is correct. And then comes the third statement, which was about the copper pyrite. Copper pyrite is CuFeS2. And this is one of the primary ores of the copper, from which copper has been extracted from very, very long time across different places across the globe. And this is having a yellowish color, actually kind of golden color. So before we come to this composition, so copper pyrite is chemically copper plus 1 oxidation state and iron in plus 3 oxidation state. So if you put Cu2s.Fe2s3, the chemical formula turns out to be, or you can say the molecular formula turns out to be CuFe2s4. So this can be considered as the empirical formula of the copper pyrite. This is sometimes also called as Chalcopyrite ore, and that is having similarity in color to the gold. So sometimes it is confused with fool's gold or actual gold. It is important to note here that in the copper pyrite, the oxidation state of iron, it is +3 and not +2, as number of different people might be confused in different setups when they do not pay close attention. They are of the view that in CuFeS2, copper is in +2 oxidation state, iron is also in +2 oxidation state, and sulfur is in -2 oxidation state. That is not true. You can find that in maybe some different questions elsewhere. Okay, moving further, we know this is also called chalcopyrite, and that basically is coming from the two words, chalco for copper and pyrite for the striking fire. That's what this is. Like if something is burnt, then it may be appearing as yellow in color or golden in yellow. That is what was the reason behind the name chalcopyrite. Okay, moving on to our main question, that this copper pyrite was heated in reverberatory furnace. Now, this is the setup of the reverberatory furnace, where we are having, this is basically the cut hole from this right side. This is the peephole, which is used to see the contents, what is going on inside. And here we are keeping our metal, which we can be heating, and basically ore we can keep number of times. There, metal purification also has been used from this reverberatory furnace, and sometimes we are using processing of ores, which was done traditionally for copper. And here we are using sand as the sand bed, which can be also serving as the acidic flux. Here we are heating the fuel, which can be taking oxygen from on the outside. This is the oxygen inlet from here. So fuel is being burnt, and those flames which can be rising here, and then they can be going back. So the reverberatory term actually implies the fuel fumes which are coming, they are not directly heating the contents, the ore or the metal. They are vapors, the hot gases which are coming over here, which can be reflected from the surfaces. They will be heating your metal samples or the ore samples. That was the main purpose behind reverberatory furnace. And here from the hot gases or flue gases are going out. We are using air damper here to control the airflow, so that if you are allowing air from here, then the suction pressure from that side may be less, than the rate of the flow burning of the fuel can be controlled from this side of the air damper, as well as from the inlet from the left side as well. That has the diagrammatic sketch of the reverberatory furnace. Now coming to the characteristics, what is there? So this furnace has been used actually from very long, about 1600 BC in China, very old, and this is actually going to be very less efficient, and this is heating by reflection. No direct heating is involved. So there can be actually sometimes problem associated when you are heating your ore sample directly in the presence of the fuels, because sometimes fuel can be interacting with your ore samples or the metal particles, and there can be some unwanted reactions. So we have chosen this. In fact, this may have even wider applications. So like we are having one condition. If you want there is no reaction taking place of the reducing things which are present in your fuels number of times with the ore or gangue particle. If you don't want that to happen, if you want to protect your metal or your ore or your gangue particles from the contents of the fuel, which may mostly be carbon based, or sometimes rarely it can be hydrogen based as well, you want to protect your things from the direct contact of fuel, then this is the best choice. Otherwise, if you think about the blast furnace, there things are coming in direct contact with the whatever that reagents we are using. Also, we understand that the oxidizing environment is present in this reverberatory furnace. We'll be seeing this, what is happening to the chalcopyrite or the copper pyrites when we are putting this in the blast furnace during the process. So the sand bed over here, which was present, that is going to serve as the acidic impurity, which can be reacting with the more basic or more metallic compounds, which can be present as gangue in your ore, and which can be preferably be converting into slag during the metallurgical operations. That was about a reverberatory furnace. Now going back to the copper pyrite. So when we are heating this copper pyrite in reverberatory furnace where oxidizing environment is present, that means because there is oxygen present, CuFeS2 will be undergoing oxidation. But we have to be a little bit careful. Careful about what? Fe3 during this reverberatory furnace, during this roasting process or the partial oxidation process, Fe3 plus will be converting into Fe2 plus as well. This is basically a reduction of ferric ions. But at the same time, there are sulfide ions present. For these sulfide ions which are converting to sulfur dioxide, this is going to be oxidation. So what will happen, because we are using over there some sand as well, in our copper pyrites, whatever amount of iron would have been present, that will be combining with the silica, and this will be converting into FeSiO3, which is being converted into slag. And the slag can be removed from the metallic copper, which we are calling matte in the metallurgical operations of the copper pyrite. And Cu2s, which may be partially converted into Cu2O during reverberatory furnace when we are heating it. Then these two things, Cu2s and partially oxidized Cu2O. And please note, copper plus 1 is not being oxidized. That is still remaining same as copper plus 1. These things can be combining with each other, and then copper may be undergoing oxidation, undergoing reduction from +1 into 0 oxidation state, and the sulfur from -2 goes into sulfur +4. So that's going to be again a redox process in which sulfur is being oxidized and copper is being reduced. So these are the processes, changes involved in the copper pyrite. So in the second statement, what they asked, in the third option number C, what they asked, when copper pyrite is heated in reverberatory furnace along with silica, iron is removed. It is true, iron will be removed as iron silicate. Sometimes we are calling that as that slag, and that slag is being removed. So copper is now going to be obtained in the pure amount. That is what was done traditionally for copper pyrite as well. Okay, a few more important points about the redox changes involved. We know that iron 3 plus is mild oxidizing agent. This can oxidize sulfide because sulfide is a reducing agent. So if you are heating the contents, ferric ions may convert sulfide into sulfur or sulfur dioxide depending upon the availability of oxygen from any source, maybe hydroxide or water or whatever sources may possibly be, as you see happening in the qualitative analysis when you are passing hydrogen sulfide to group number 2, then if iron was present in your sample, that is supposed to be converted into ferrous. Now that ferrous in group number 3 was supposed to be oxidized by diluted H2O3, then only we can do the test of iron as iron 3 plus in group number 3 in the qualitative inorganic analysis. So this reaction, ferrous plus sulfide, is going to be a redox change, no doubt about that, but there is a little problem. The problem is all the sulfide ions, when they are converted into SO2, they will be requiring more number of electrons than iron 3 plus can provide, because Fe2S3 there are 2 Fe atoms and 3 sulfur atoms. All the 3 sulfur atoms, if you put together, this change of sulfur is going to be like this. Sulfur is -2, this is converting into +4, so there's a 6 electron change involved. This is going to 6 times 3, that has to be 18 electrons loss is associated when sulfide is converting into sulfur dioxide. But when only 2 Fe3 plus ions will be converting into Fe2 plus ions, this is gain of only 2 electrons. So all the ferrous, all the sulfide ions present in the Fe2S3 are not possibly to be oxidized using that Fe3 plus present. We need some external source of oxidizing agent, and that's why we need oxygen as well. And that's what is here, that oxygen is required. Air is required in this inlet sample, which will be oxidizing our ore if it was present as copper pyrite. Like here, instead of metal, if it was CuFeS2, then without that oxygen, we cannot get the copper metal in the final stages. Okay. So this statement was basically true. This is little bit about the redox processes, what is happening when copper pyrite is being heated or it is being roasted as per se in the reverberatory furnace. So fuel, what we have been using traditionally in reverberatory furnace was wood. Coke can also possibly be used, but that's not giving very volatile, not being very much volatile in nature. This is not giving enough flames which can be effectively used to heat your that ore samples or the metal samples. So mostly wood has been used, but the important thing is this is not coming in contact with FeO, because FeO can possibly be converted into metallic Fe if you are using carbon in contact with that. That is the situation what we have seen in the blast furnace happening in the metallurgy of the iron as such. So to remove iron, we can use reverberatory furnace in a much more efficient way, rather than we could have used this in the blast furnace, where iron was also finding a chance to get converted into metallic iron, which will be going as the impurity in your copper. Then in later stages you need to purify that. You may be requiring even more energy involved in those further processes associated. That is what was the use of reverberatory furnace, that is was done for the extraction of copper from the copper pyrite. That's all for this option number C, and option number C stands to be correct. Talking about the option number D, this is one of the earliest mentions of the leaching processes. So this leaching was supposed to be done by keeping these different ore samples into larger heaps, as you can see over here in the part number B, and those larger heaps were supposed to be traditionally sprayed with water. Some biological oxidation or environmental agents which could possibly be present, they could have helped that leaching process of those different samples. It was done traditionally for copper and silver and gold as well. Copper, more importantly, this hydrometallurgy was supposed to be done. So this is one of the very basic understanding of the leaching process, and this diagram is taken from De Re Metallica, which was written in Latin by Georgius Agricola, and we are having English translation of that available as well. That book was very long back in 1556. We were having very little understanding of the metallurgical operations. Then these things were described by Georgius Agricola, that the rocks were piled up in very height, and then when water was sprinkled over there for 40 days, then the rock will begin to fall into pieces like slag, lime, and that originated new material. So basically those effluents which were there, those were leached samples, and from those leached samples the different metals could have possibly been extracted. Coming back to our method, which is MacArthur Forrest cyanide process, in which we are extracting silver using potassium cyanide or sodium cyanide. So this process is basically developed. This was developed by Stuart MacArthur Forrest in 1887, and this was done for extraction of low-grade iron, as it was done for the sulfide ores using froth flotation process. The MacArthur Forrest is the equivalent of the gold metallurgy, which was the as for the copper's metallurgy, from low-grade copper, extraction was made profitable by froth flotation process. From low-grade gold ores, extraction of gold was made profitable by this method, MacArthur Forrest cyanide process. Okay, and this is him, MacArthur Forrest, and this process was based from the idea from the Scheele, who for the first time told that gold is soluble in sodium cyanide aqueous, and there were people like Bagration, Elsner, and Faraday who discovered that the gold atom in this complex which is being formed, one gold combines with two cyanide atoms. So this stoichiometry was also known. So Forrest continued that idea, and he modified those different operations, and he came up with this idea that if cyanide samples of if the cyanides are used for the leaching of the low grade gold ores, or even that can be used as such for the silver ores as well because of similarity in their chemical properties. So this is the basically structure of that compound which that MacArthur Forrest cyanide process results into. Here we are representing this gold, that's your copper, sorry, that's carbon, and that is your cyanide. So this is a cyanide ions, and this is the gold. That same kind of structure exists for the argento cyanide, that is silver cyanide as well. This is oro cyanide, which is for gold cyanide. Now, the overall reaction what this MacArthur Forrest cyanide process involved is called as Elsner reaction. That's this reaction. So this metal can be either silver or it can be gold. So we require aqueous solution of cyanide. Quite dilute solution is sufficient enough, and we require the presence of oxygen. So then metal is oxidized from the 0 oxidation state into +1 oxidation state, and this becomes soluble in water. And then we use this process further to get this metal, either gold or silver, back in the later steps when we are reducing it with the zinc, which is quite reactive, and that displaces copper from this complex. That replaces gold and silver from this complex, and that zinc being more reactive will be replacing these two things. So this is the flow chart for the extraction of gold, quite long. I'm not going into detail. You can just have a look how this crushing ores can be used. Here is the cyanide leaching which is being done. That is the key step, and then subsequent steps are going to give you ultimately the gold as the pure sample. We call those DOR as the extracted gold, which may be having whatever good percentage of the purity of the gold. Silver also can be doing. We can be processed the same way. So the sequence of reactions which we are seeing over here for gold, silver also will be following the same pattern, and the cyanide source of cyanide we have been using as sodium, potassium, or sometimes calcium also has been used in this process. And for both the metals, silver and gold, we can be using these methods. And these are the reactions basically. Step number 1, step number 2, step number 3. We'll be taking these steps one by one. So starting from the metal, we are getting that metal cyanide, which is converting into complex and which is converted back into the metallic solid in the subsequent steps. Here we go in these steps one by one. So first step is alkaline oxidation of silver. So this is whatever metal we are having, the silver we are assuming, this is 0 oxidation state, and this oxygen is oxidizing it. We understand the oxidation factor of oxygen is, the N factor of oxygen is 4. When this is going from 0 oxidation state into -2 oxidation state. And N factor of metal is supposed to be 1 because this is going from 0 to +1 oxidation state. So we understand when N factor are 1 and 4, the balancing factor is crisscross required for that is going to be 4:1. So 4 metals are oxidized by 1 oxygen, and we are getting this metal cyanide. This metal cyanide, which is being formed in the subsequent step, undergoes complexation. We know that transition metals can form the complexes very easily, and cyanide is one of the very strongest, like it's very strong ligand. It is lying on the higher side after carbon monoxide only in the spectrochemical series. So this can form the complexes very easily. This is the complex being formed and which is soluble. So this soluble complex can be extracted from the rest of the ore sample, low grade ore sample, which may not be soluble, which will be remaining behind. This thing which is running off as leached solution can be used for the extraction of that silver or gold in the subsequent step, which is the reduction of the silver complex. So this silver complex is having in +1 oxidation state, and this is being reduced because here zinc was 0 oxidation state, zinc is converting into +2 oxidation state, and here metal is converting into from +1 to 0 oxidation state. So again, n factor of zinc is going to be 2, and n factor of this metal is going to be 1. So we require this ratio as 2:1 rather than 1:2. That is the reaction which is involved in these steps. And if you put all these steps together, we are representing this as Elsner equation. And this is the overall step, first two processes, and then we know like the first two processes put together are sometimes represented as Elsner equation after his name. So the actual mechanism, although we have written here with respect to oxygen, actual mechanism is known to involve hydrogen peroxide as an intermediate. So if we have hydrogen peroxide, basically in the very first step, when oxygen is being used, there is involvement of hydrogen peroxide. This hydrogen peroxide is being consumed in the subsequent step, and you are getting again the same kind of product. So the final equation, that Elsner equation would be written, this is turning out to be the same, although in different representations which we might have been seeing earlier, maybe looking like the very first one. So that is your Elsner equation, which is basically having involvement of hydrogen peroxide, which in most of the times we are not seeing. We are just starting the reactants products. We are not involving hydrogen peroxide. And in actual metallurgical operations, it has been found that they are sometimes increasing the rate of the leaching process by introducing more and more of the hydrogen peroxide, which has got one extra advantage, that this is going to be relatively involving greener chemistry, because hydrogen peroxide, even if it's remaining behind in the leach solutions, this is not going to create much of the problem, because this decomposes very quickly in presence of sunlight into water and oxygen, which are not at all toxic to the environment. That is the part of green chemistry as well. So coming back to our main question, these were all the 4 options, A, B, C, D, and having discussed about all these options, now you understand fairly well what was the situation, which all options were correct. Option number A only was not correct option. Option number B, C, D were supposed to be correct options, right? That's all in this video. It was such a huge video. Thank you for giving your time. This was actually a very, very long video, much longer than expected. And I hope this was worthwhile spending this much time on this video. You might have learned a lot, many things with respect to metallurgy. If you really feel this was useful to you, please consider liking and subscribing this channel, and stay tuned for more such videos. Thank you. Bye-bye. Take care.